Let's start today's class. So, in the last class, we were discussing about what all are the advantages of using a feedback in a control system. What advantages and how the dynamics or the system parameters they are changed when we are using a feedback system. So we saw that while if we are using feedback, then obviously there are advantages like it can reduce any kind of parameter the effect of any kind of parameter variation which is happening in the system because of some external factors that can be reduced if you are using a feedback mechanism. Also, if you have some kind of the sensitivity of the system due to these kind of changes, that sensitivity is also reduced by using feedback. So then we started to discuss about the system, how can the system dynamics be controlled by using feedback. So in the last class we were talking about like if you have, let us say you have a system whose the forward path transfer function is given by k dash by s plus alpha. So in case if you are dealing with an open loop system, so that means this feedback path is not there. So then you can write that the transfer function gs will be equals to some k by, let's say, tau s plus 1. Okay, so from here you can say, or from the first expression you can say that the pole of this system is at, so for finding the pole what you have to do is that you have to make the denominator polynomial equals to 0 and you have to find the roots of the denominator polynomial. Okay, so here the denominator is s plus alpha, so you make s plus alpha equals to 0, so s equals to minus alpha. So that means the pole of the open loop system lies at s equals to minus alpha and the time constant of the whole system is given by tau. Okay, and also that if you see the DC gain of the open loop system, that is equals to k. So now in the second case, let us now make this loop, let us close this loop and have a unity feedback system. So now the system looks something like this and it has a unity feedback. So if you have an unity feedback, then similarly you can write again, you can write that equation for the transfer function of the whole system. And so if you write the equation, you see that gs now comes can be expressed now by this term. In the numerator you have k by 1 plus k and the denominator you have tau c s plus 1, where tau c is basically the time constant of this closed loop system and the value of tau c is given by tau by 1 plus k. So that means the value of the time constant which was present during the open loop system. So now the time constant has the time constant is getting reduced by a factor of 1 plus k. So for the open loop system, the time constant was some tau, and for the closed loop system, the time constant is less, and the factor by which it reduces, that is equals to 1 plus k. Similarly, if you see the pole position, you see now that the position of the pole is s equals to minus alpha plus k dash. So that means previously if the pole was at some, if you draw this, so if the pole was at some position here, so this was, let's say, minus alpha. So now the pole has shifted farther left and now the current position will be minus alpha plus k dashed. So this is the pole position in case of a closed loop system. Also, if you observe the DC gain of the closed loop system, you will see that the DC gain has also reduced and it has reduced by a factor of so it has reduced to a value k by 1 plus k. So so that means after using feedback, the pole of the system shifts, the time constant reduces and the DC gain also reduces. Now we'll see what does this thing mean, that the time constant is reducing means what, like how is the system dynamics getting affected by that. So now let's say that you are exciting the same system using an impulse input. Okay, so impulse input means RT will be equals to del T, and if you take the Laplace transform, RS will be equals to 1. So now if you see, if you substitute RS equals to 1 over here, so that means CS will be nothing but CS will be equals to this term GS. Similarly for the open loop system, CS will be equals to K by tau S plus 1 only because RS is equals to 1. So now if you want to find out what is the time domain characteristics or how the system response is changing with time, then what you have to do is that you have to take the Laplace inverse of that expression of the transfer function and then you will get the final output of the system. Okay, so here we'll just go through this step once, because later on we'll be discussing in details about this time domain characteristics of control systems and how they are affected by various parameters. Those will be dealt later on, but just for now, just to have an idea about how this feedback is actually affecting your system dynamics or the response of your system. So now for this open loop system, so the value of the output CT will be equals to Laplace inverse of K dash by S plus alpha. So you can write that is equals to K will be equals to K dash e to the power minus T by tau. Okay, and similarly for the closed loop system, the value of CT will be given by K dash e to the power minus tau by minus T by tau C. Now, if you draw this on this, if you draw the or if you plot the values of CT for both the open loop and the closed loop response, so you see that for the open loop system, so this is the value, this is the response where, so this is for the open loop case and this is for the closed loop case. Okay, so the difference you can see visually is that the system is decaying much more faster at a faster rate when you have a closed loop system, and the system is decaying at a slower rate when you have an open loop system. So that means, initially we saw that the time constant of the closed loop system is less. So time constant of a system is less. That means that it will decay at a, or it will exponentially decay at a faster rate. And similarly, from this response, you can see that since the value of time constant is more, so that means the response will take much longer time in order to reach a stable value. Okay, so the effect of using a feedback is that the response of the closed loop system that decays faster, but there is a problem that the effect of feedback the presence of feedback might affect your system adversely, because it might trigger instability of the system. So it might so happen that your open loop system is a stable one, but the moment you make you use a feedback and use a closed loop system, depending on what all are your system parameters, it might so happen that the closed loop system becomes unstable. So this is just a fact that you need to like remember as of now. We will see like some examples of how this thing can happen maybe later on. Okay. So now then comes the effect of feedback on a bandwidth of a control system. Okay, so bandwidth means, so first of all, let us consider a control system which is represented by a low pass filter. Okay, so bandwidth of a system is defined by the frequency range in which the value of the gain drops to 1 by √2 of its DC value. Okay, so if it is a low pass, in case of a low pass filter, the system responds to frequencies up from DC, starting from DC up to a certain value. So let us say that that value is given by omega b. So at omega b, what happens is that the gain of the system drops down to 1 by √2 of its DC value. So this frequency omega b is known as the bandwidth of the system. So if you have a larger bandwidth of the system, so that means the system responds very accurately to higher frequencies. Okay, so if you have so that means if you have very fast changing signals, so higher frequency means the signals are changing in time at a very fast rate. So that means if your system has a large bandwidth, so it implies that the system will respond accurately to higher frequencies, and higher frequencies as in very fast changing signals. Okay, so now let us say that you have that similar kind of system. You have the closed loop, the open loop system as well as the closed loop system. So if you write the equation for G of j omega, so the transfer function for open loop system is G of j omega equals to K by, here we are writing in terms of we are replacing S with j omega, because here we want to find out what is the value of the frequency. Right, so you are substituting S by j omega, and we can write that G of j omega is for the open loop system K by j omega tau plus 1. Now we know that for at the bandwidth, the highest frequency which is considered as the bandwidth, so at that point the gain drops to 1 by square root. So if you write the gain if you take the magnitude of this transfer function, you will see that if at 1 by root 2 of that becomes, so this is the equation for finding the bandwidth. So from here you can write that for the open loop case, the bandwidth is equals to 1 by tau. Similarly, for the closed loop system also, you can find the similar kind of equation, and you can see that the closed loop system, the bandwidth is given by 1 by tau c. Now, if you take a ratio of this open loop bandwidth by the closed loop bandwidth, just to have a knowledge about how the bandwidth is changing when we are moving from a open loop system to a closed loop system. So for this, if you do take a ratio of the bandwidth for closed loop system to the bandwidth of the open loop system, that is given by 1 plus k. So that means that the closed loop system has a much higher bandwidth compared to the open loop system. So that means if you have a closed loop system, so that means that the speed of the so it will respond to a much larger range of frequency inputs that you are providing, and the speed of the response will also be faster in case of the open loop in case of a closed loop system. Okay. We will see, like we have talked about that using this feedback mechanism, we can nullify or we can eliminate effects of noise and disturbances which might be there in the system. So now let us consider we have a transfer function, an open loop transfer function which looks like this, and there is some noise signal or some disturbance signal which is coming at this point. Okay, before this transfer function GB, there is some noise which is unwanted noise which is coming into picture. So now we will see what is the effect of this noise on the output. Okay, so for finding out that, what we need to do is that first of all we will write the transfer function. So transfer function means, now since we want to see the effect of a noise on the output, so here what we need to do is that we need to consider that there is no input, so the only input to the system is NS. Okay, so we'll consider only input as NS and we'll make RS equals to 0. So if you write the expression for CS by NS, considering that NS is your input now, even though this input is not a desirable input, but still, since we want to see the effect of this disturbance on the output, so you will write CS by NS for the condition when your actual input RS is equals to 0, that will be given by GB of S. So this is for the open loop system. Okay, and in the second case, now what we are doing is that we are closing so this is the open loop case, and in the second case we are closing, we are using a feedback. So the feedback has a value of H. So using this feedback we are making this system as a closed loop system. Now for this closed loop system, if you write the expression for CS by NS, again for the same condition that the value of RS is equals to 0, then you will get that CS by NS for RS equals to 0 will be equals to GBS by 1 plus GA GB into HS. Okay, so if you compare this equation, the open loop equation and the closed loop equation, you see that in case of a closed loop equation, the output which we are getting due to the noise, if noise is considered as the input, that is much less when you have a feedback mechanism in play. Whereas when you don't have any feedback, then the output CS will be given by GBS into NS, right? So that means the effect of NS will be more pronounced when you are dealing with an open loop system. But the moment you are going to the closed loop system, so the effect of this noise on the output, that will be reduced by a factor of 1 plus GA GB into HS. So that is one of the one of the other advantages of using a feedback mechanism. So using this feedback, you can see that if you have any kind of unwanted signals like noise or disturbance in the system, so that effect of that noise or disturbance, that will be reduced to a great extent if you are using a closed loop system. Okay. Also, we need to understand at this point that if you want to have a very optimum performance of the system, then you have to choose this measure. So this HS is basically the feedback sensor or the measurement sensor, you can say. So you have to choose the feedback sensor in such a way that the value of HS is maximum, and so that you can reduce or the signal to noise ratio of the sensor can be improve to a large extent. So for choosing this what is the criteria for choosing this value of H? So the design specifications is that the Hs should have very low parameter variations. So it should not be affected by any kind of external environments. Such that it is sort of, because previously we saw that any change in this or in case there is any variation in the feedback sensor, so that gets directly affected, directly reflected on the output. So that means we have to make sure that this feedback sensor that we are using, that is not changing with the, that has very low parameter variations. And also obviously for better measurement, we have to have the signal to noise ratio should be very high. So now we'll see, so these were sort of some of the effects of feedback. Now this feedback also have another kind of effect which is known as the linearizing effect. So linearizing effect means, so what we'll do is that, let us say that we have so linearizing effect means the feedback, so if you have a non-linear function, then using a feedback, you can approximate the system as a linear system. As you all know that if you have a linear system, it becomes much more easier for analyzing that system as compared to a non-linear system. Okay. So now let's say that you have so this is the system that you have. Okay. So let us say this block is some function, some transfer function is there. Okay. So this is output. And we are using a feedback, a unity feedback. So the input is, let's say, R. So you have plus minus over here, and this is the error signal E, and this is not E, this is C. Okay. So now let us say that this transfer function, that is a non-linear expression. Okay, non-linear expression as in, let us consider that the value of f here, where E is the input for this block and C is the output of this block, and this expression is given by f of E is equals to E square. So E square is basically a non-linear function. This is not a linear function. So that means if you have an open loop system, then the value of C will be equals to f of E. So f of, now E is nothing but, in case of an open loop system, E is nothing but R. So that means output C will be equals to R square. So once you have C equals to R square, you can say that this is a non-linear. This is a non-linear equation, right? And now if you have a closed loop system, so in case of a closed loop system, so this C is coming over here. So that means the value of E is now changing. So now E is equals to R minus C, and this function of E will become R minus C whole square. And so this R minus C whole square will be equals to the output C that you are getting. Okay. So if you are getting, now if you draw the, so let us say let us draw the functions. So you have, in case of an open loop system, so let's say this is the output C and this is the input R. Okay. So in case if you have an open loop system, the response, or it looks something like this in case of an open loop system. Okay. But the moment you have a unity feedback system and you have this expression, so then if you plot the value of C, then you will see that it is not, if it's not exactly linear, but it is linear in a very wide range of, so this is the closed loop response. So the input output relationship, that is approximated as a linear relationship over a wide range of input variables. Okay, so in case of an open loop system, so this was a clearly non-linear expression was there, non-linear relationship between the input and the output. But the moment you are using a feedback mechanism, the output, the input output relationship, that can be linearized over a large range of the input variables that we are providing. So this is another effect of this feedback. Is there any doubt till now?
No, ma'am.
Okay. Till now, we were mostly talking about negative feedback systems, right? Negative feedback systems means in case in the comparator, whatever was coming from the output in the comparator, that was going into the negative sign. So that means we were subtracting, or we were taking the difference between the reference input and the output that we are getting from the feedback sensor. Okay, so now instead of a positive negative feedback system, you can have a positive feedback also. So positive feedback means you can just change the sign. So in case of instead of using the difference between the reference input and the output of the feedback sensor, what now you will do is that you will take the summation of the two signals. Then it will be known as a positive feedback system. Okay, so positive feedback system is also known as like regenerative feedback. So what is done over here is that the output which is fed into the feedback with a positive sign. So that means the set input, which is the reference excuse me, the set point or the reference input and the output values, they are added together, and that summation of that is fed to the controller. So the feedback is basically in phase with the input. Okay, so this is the diagram of a positive feedback system. So if you write the transfer function of the positive feedback system, so initially for a negative feedback, so for negative feedback system, the output CS by RS was equals to GS by 1 plus GS HS. But in case of a positive feedback system, the expression changes. You can derive this expression starting from the basic rules, like you take, so here it is CS into C into H. This is the output E. And similarly, you can from the basic equations, you can find out what is the transfer function of this positive feedback system. So so it shows that CS by RS will be equals to GS by 1 minus GS into HS. Okay. So now, why do we want a positive feedback system? Okay. So the effect of this positive feedback system is to increase the loop gain. Here you see that you have 1 minus some GSHS. So that means the denominator is less than 1. So the overall gain of the closed loop system, that increases. So that can be one of the advantages of a positive feedback system. So it can be used to increase the loop gain of the system. So that means the overall gain of the positive feedback system can be will be greater than the open loop gain. Okay, so the open loop gain was only GS, but in case of a positive feedback system, the overall gain becomes greater than the open loop gain. Okay, so this is one advantage, but again there is a flip side of the coin also. So since you see that the bottom in the denominator, it has a negative sign, so it means there is a chance that the denominator might become 0 if the value of GS into HS is equals to 1 or becomes closer to 1. So that means the denominator will become 0. So the moment the denominator becomes 0, so that means what? That for any kind of input that we are providing, for any finite input that we are providing, we will be getting an infinite output, which is not possible. So that means that if you are getting an infinite output for a finite input supplied, so that means that the system is not stable. So what we can do is that, so this is like the disadvantage of using a positive feedback system. So now like what you can do over here is that, like, so then where do we use this kind of positive feedback system? So let us say that if you have like in a system is designed in such a way that it has multiple loops. So as of now, so in this mechanism you saw that there is only, in this figure, there is only one loop. So there is only one feedback sensor and there is a single loop present in this control system. But let us say that if you have a system which has multiple loops, in case of that, if you have the inner loop of the system, if it has a positive feedback, then the overall closed loop transfer function, that becomes insensitive to the changes in the forward path gain. So let us take an example. So first, let's say that you have, so this is your RS. So in this loop, you see that there are two loops. One, so this is the inner loop. So this one is the inner loop. And the outside there, this is the outer loop, you can say. So this is like a multiple loop kind of an system. So if you see that the inner loop, it has a positive feedback because this is going to the plus. So that means the transfer function, if you write the inner loop transfer function, so it will be equals to 1 by 1 minus GF of S, right? And if you replace this inner loop with this transfer function, then you can write the overall transfer function. So now, so what we are doing here is that we are replacing this with this transfer function. Okay, so then you can write the overall transfer function will be equals to G by 1 minus GF divided by 1 plus GH by 1 minus GF. So which will be equals to G by 1 minus GF plus GH. Okay, so now if you, so this is the overall transfer function. Okay, so now if you take the value of GF, let's say it is approximately equal to 1. So if that is the, if you select the feedback sensor for this positive feedback loop as approximately equal to 1, so then you can write that the overall transfer function that becomes approximately equals to, so this term gets cancelled out, so G by GH. So this will be equals to 1 by H. Okay. So the moment you have for this kind of an condition, so the overall transfer function, you see that it becomes independent of the forward path gain. It is only dependent on the feedback path gain. So you can say that if in case when you, so that means it is, since it's not dependent on the forward path gain, so that means if there are any changes of, or there are any insensitivities present happening in this transfer function G, so that will not be affecting your output. So that means here, even though we are using a positive feedback system, so then this it results in a, so it results in a system such that the output becomes insensitive to any kind of variation in GS. So these are mostly the different applications or different advantages of using a feedback mechanism in a closed loop system. So now we'll move on to, okay, so before going to that, so what I want all of you to do is that I'll give you some examples and I want you to solve this problem. So the first example is that you have a unity feedback control system and the forward path gain is given by this transfer function. Okay, so that is equals to 25k by s plus 5 and the nominal value of k is given. Now what you have to find out is that you have to find out what is the sensitivity of the closed loop transfer function to any kind of variations in K. So can anyone tell me how you want to, how you would you proceed for solving this problem? So what will be the first step? Anyone? Anyone is there in the class?
Yes, ma'am.
Okay, so can you tell me like how would you proceed for solving this problem? What would be the first step?
Ma'am, I have no idea, ma'am.
So just read the question, and just by reading the question you can find out like what should be the first step. I'm not asking you what is the mathematical expression or anything. Just read the question. What is given and what you have to find. Just tell me that. What is the given thing?
Ma'am, we have a transfer function here given to us of a system.
Yeah.
And nominal value of k is given to us.
So the transfer function which is given, what kind of transfer function is given? Is it the open loop transfer function given or the closed loop transfer function? Which one is given?
Ma'am, closed loop.
Why closed loop? The transfer function is written now that the forward path transfer function is TS.
Oh yes, ma'am. It's between only the forward part, so it should be open.
Only the forward path is given.
Yes,
so that means only the open loop transfer function is given, right? And you have a unity feedback.
Yes, ma'am.
So can you draw the system now? Can you draw the closed loop system now? Did I draw it correctly?
Ma'am, the feedback will be 1, no ma'am, k equal to 1.
So 1 means that's why I have shorted, no? Otherwise you just have a block and you write 1 over
Yes,
here.
ma'am, yes.
It's the same, right? So now this is your closed loop system. Now what you have to do is that you have to find the sensitivity of the closed loop transfer function. So first step would be, step 1 would be you have to find out the closed loop transfer function.
Yes, ma'am.
So what will be the closed loop transfer function? Let's say that is.
Ma'am, it will be T of S by 1 plus T of S because we have the closed loop as 1, like closed loop feedback. So T of S by 1 plus.
Yeah, so it will be TS by 1 plus TS. So this is the closed loop transfer function. Okay, so once you have the closed loop transfer function, so you can just substitute the value of TS with the given expression and you can write it in form of S. Okay, as a function of S. So now the second step is that you have to find the sensitivity of the closed loop transfer function with respect to any variations of K. Okay, so the sensitivity, as if you recall, the definition of the sensitivity was sensitivity S of any, let's say here we are dealing with G. So you have the transfer function G with respect to K. Right, so this is the sensitivity that will be given by delta G by delta K into K by G. So this was the basic definition of sensitivity, right?
Yes, ma'am.
Okay, so now since you know the expression of G, so what you need to do is that you just have to take the derivative. You have to find out the value of this delta G by delta K and then find the overall expression. Okay, and then finally, if you just substitute the value of K equal to 1, then you will get what is the value of SG of K in terms of S. Got my point?
Yes, ma'am.
Okay, so similarly, you can have, so this is another example which I would request all of you to go through this problem and try to solve. So here you have have an inverting amplifier, and what you need to do is that, so this is A. So what you need to do is that you have to find the So you have to find the overall transfer function. So T is basically, you can write T is equals to V out by V in. So you have to find out what is the value of T, and then from this T you have to find out what is the sensitivity S of T with respect to A and S of T with respect to B. And there are some parameters which are given. From there, if you at the end you will substitute these values and you will get ST of A and ST of beta. So I want all of you to solve this problem, and in tomorrow's class I want the answer for what would be the answer for this question, and I want you to tell me how you solved it. Just giving me the final answer will not be sufficient. So you have to tell me how you solved the equation and then how you found the sensitivity. Okay, so this you have to do it by tomorrow. In tomorrow's class I'll ask. Fine. So next, moving on to another topic for this. So this topic is basically the linearization of nonlinear mathematical model. Okay, so why do we need to linearize any kind of mathematical model? Okay, so as you know that any physical system, that none of the physical systems which are there present in the in our surroundings, they are perfectly linear. Okay, so all of the systems, they will have some non-linearity component attached, associated with it. Okay, but the mathematical tools which are usually available to us for analysis of any kind of system, those are mostly valid for linear kind of systems. Okay, so that's why you can see that there is a need that if you can linearize a non-linear system, so then it would become easier for you to analyze that system and then find out and then do whatever mathematical analysis that you want to do on the system. Okay, so now how do you linearize a non-linear system or a non-linear, if you are given with a non-linear equation, how do you linearize that? Okay, so the basis of linearization is that if you have a smooth curve, so the basic thing is that you have, let's say you have a smooth curve, and that curve that varies very little from its tangent line. So if you have a plot like this, so let us say your nonlinear, so this is your expression, or this is the plot for some nonlinear function. Okay, so if you take a point, let's say over here, let's say this is point P. Okay, so if you draw a tangent at this point, so if you draw a tangent at this point, so you can see that at a very close proximity in and around this point P, you can say that the variation of this signal or this function, that is very less, right? So around this, about this tangential point, so the variation of the so it does, the function does not vary much. Very much means the input output relationship that can be that can be linearized, or that can be considered to be a linear function in a very small region about this point. Okay, so that means a smooth curve differs very little from its tangent line, as long as the variable does not move far away from this point of tangent. Okay, and also, so if you have so similarly, if you draw this, so let us say, so this is your output which is given by some y, and this is your input which is given by some x. Okay, so this point is, let's say, x0 and this is y0. Okay, so the slope at this point x0 will be equals to, so if let's say y is equals to function of x, so this is the plot for fx, y equals to fx. At this point, tangent point at x0, so the slope will be df of dx at x equals to 0, x equals to x0. So if that value is equals to m, then you can write that y equals to, you can just linearize that linearize the given function fx in a very small range. So let's say this is the range. Within this range only, you can say that you are linearizing the nonlinear term. Okay, so now if you read this statement, so if a system operates around an equilibrium point and the signals which are involved are small signals means they are not changing much around this operating point, then in that case a nonlinear system, it can be approximated as a linear one. For this approximation, what you need to do is that you have to use an expansion of, you have to expand the nonlinear function into a Taylor series, and you have to, about an operating point that will be given, and you have to retain only the linear term. And retaining only the linear terms means that you are ignoring the higher order terms. So this higher order terms, they can be ignored only if the deviation of the variables are very small about the operating point. So now let's see that if you have an input is given by xt, the output is equals to yt, and the relationship between the input and the output is given by y equals to fx. Okay, and let us say that the normal operating conditions are x dashed and y dashed. So now if you do the Taylor series expansion of this function y equals to fx, so that can be written as y equals to fx will be equals to f of x bar plus x minus x bar into df dx plus x minus x bar whole square by 2 factorial d2f dx2, and so on and so forth. There will be multiple other higher terms. Okay, so all these derivatives, they are all calculated at x equals to x bar. Okay, around at the operating point. So now if you have, if you consider the case where the value of x minus x dash, that is very small. So in that case, you can ignore this higher order terms. So x minus x bar, if it is very small, so that means x minus x bar whole square will be even more smaller. So what you can do is that you can ignore this higher order terms, and you can just write y will be equals to, you can just retain the first and the second term, and you can write y will be equals to fx bar plus x minus x bar into df dx. Okay, so now you can just, f of x bar will be nothing but y bar, because for x bar the output will be y bar. So you can write y minus y bar, y equals to y bar plus, let's say if the value of df of dx at x equal to x bar is given by k, then you can write that plus k into x minus x bar. So if you write this equation, so this, you see that this equation is basically a linear equation. So that means that the relationship between the input, so this is the input and this is the output. So after doing this Taylor series expansion, we are getting the input output relationship is now has become a linear one. So y minus y bar equal to k into x minus x bar. So this is one way of linearizing a non-linear mathematical expression. Okay. So another alternate form of this Taylor series expansion is that in the first case we saw that, so now let us say that the value of x equals to a plus h. Okay, so now if you have y equals to fx, so that will be equals to f of a plus h, and the value of h is equals to x minus a. So similarly, if you write the expression for y equals to fx, so y equals to fx will be equals to f of a plus h, and then you can just expand it. So it will be f of a plus h into df dx plus h square by 2 factorial d2f dx2, and so on and so forth. Okay, so from this again, if you if the value of h is very small, you can just ignore these and the all other higher order terms. So you sort of neglect these terms if h is provided h is very small. Okay, so then you can just write that y will be equals to f of a plus h into df dx, which is nothing but a linear equation. So now let's say that you have been given an example of y equals to fx, which is equals to x squared minus 5x plus 7. And you need to linearize this function with respect to x equal to 5. Okay, so the normal operating condition is given as x equal to 5, and you have to linearize this function. So then how can you do that? So this is the expression that is given, and you have to find out what is the value of this y equals to, you have to linearize this function, non-linear function x square minus 5x plus 7 with respect to x equals to 5. So that means if, so the value of a here is given as 5. Okay, so if a is given by 5, if you write this expression, so y will be equals to f of 5 plus h, you can write x minus 5 into df dx, which is calculated as x at x equals to 5. So what will be the value of f5?
Ma'am, 7.
f5 is 7. Fine. Then, and what is the value of this df dx at x equal to 5?
Ma'am, it's 0.
0. Why?
Ma'am, 5 minus 5, 0, ma'am, there, if x equal to 5.
No. So, sorry, actually this will not be x. So this is like a equals to 5. So x here is the variable. So this is basically the value of a, the operating point. X is the variable.
Yes, ma'am.
So you have to find y as a function of x.
Ma'am, then 5 will get.
So then df dx will be equals to 5. So then final expression, how will it look like?
We'll get 12, ma'am.
12.
df by dx at x is equal to 5, no, ma'am. So differentiating, we'll get 7 plus 5, 12.
Then where will this x minus 5 term go? f5 is equals to 7 plus you have this term, na, x minus 5, and then you have got 5 over here.
Yes, ma'am.
Okay, so that means this will be equals to 5x minus 18, because at the end you have to find out what is the relationship between y and x. So you cannot substitute x with anything. So x has to be there, y has to be there, x has to be there. But instead of this non-linear equation x square minus 5x plus 7, now what you have done is that you have linearized this equation and you have expressed it in terms of in a linear form like this. But the operating condition is that you can say that x0 or a is equals to 5. About this point, if your operating condition is x equals to x0 is equals to 5, at that point the value at that point you can write you can substitute the nonlinear equation as a linear equation y equals to 5x minus 18. Okay. Okay, so this was the expression where we had only one the function of so y was dependent only on one input. Okay, so now if your value of y is dependent on another, like there are two independent variables x1 and x2. So then if you if you again do the Taylor series expansion, so you will see, and now the operating conditions are x equals to x1 bar and x2 is equals to x2 bar. Okay. So about these operating conditions, we want to linearize this function. So now you can write y equals to f of x1 bar comma x2 bar plus similarly, so you will have two terms. So now since there are like two independent variables, now we will have the partial derivative instead of normal derivative. So you have x1 minus x1 bar into delta f by del x1 and so on and so forth. And now since we are assuming that around this operating point, that is x1 bar and x2 bar, the variation is very small, so you can ignore these higher order terms. So these higher order terms can be ignored. So if you ignore these terms, then you will write that you will get y will be equals to nothing but f of x1 bar comma x2 bar and this expression. Okay, and similarly if you just substitute this delta, this partial derivatives with some constant k1, because they are calculated at the values of x1 bar and x2 bar. So you will get two constants and you will see that this is the final linear equation from this around this operating condition. Okay, so similarly if you have like more than two variables also, you'll just have to write the Taylor series expansion, and from there you just ignore the higher order or the second order terms, and you will land up with a linear equation between the linear relationship between the input and the output. So this is another example. So where the operating conditions are given 5, 4. So that means x1 bar is given as 5. And x2 bar is equals to 4, and what you need to do is that you have to again linearize this function, and you have to find out what is the linear form. Okay, so this is also I want you to solve and then give me the answer in tomorrow's class. So now we are left with only one more topic, which is that of a nonlinear spring. So this nonlinear spring, so that means here also the spring are basically any spring is not linear over any arbitrary range of expansions or extensions. Okay, so any kind of so if you want to see a linear spring, so the relationship of the spring will be equals to the force applied will be equals to the spring constant K multiplied by the displacement or the extension of the spring. Okay, but this linear law that is applicable only for a limited range of extension. Okay, so if the value of y is measured beyond the for sort of like for large extensions, so if the value of y is very high, so in that case this linear law is no longer followed. It becomes the spring follows a nonlinear equation. So that means the force will become equal to k into y square. And this is a nonlinear equation because this does not satisfy the principle of superposition and homogeneity. That's why that's a nonlinear spring that has two ranges of operation. One is in the linear range, another one is in the nonlinear range. Okay, so now from this nonlinear range, so let's say we are considering a spring mass system like this. Okay, so now the gravitational force is going downwards. So and the expansion is also in the downward direction. Okay. So if you draw the free body diagram and you write the expression for this nonlinear spring, so you will end up with this equation. Mg will be equals to m into y double dot plus f into y dot plus k into y square. So you have a spring, you have a viscous friction which will act as a damper, and then you have the mass, which is you have the gravitational force. So that means, so this is your equation. Okay, so what we consider here is that if you have a steady state condition, so that means that at a steady state condition all the derivatives of the output will be equals to 0. So that means this term and this term, this will become 0. And if your steady state condition is given at a position y is equals to, so steady state is at y equals to y0, then you can write mg will be equals to k into y0 square. So the value of y0 will be nothing but square root of mg by k. Now let us say that the value of y, it changes by a small value delta y about this steady state condition y0. So you can write that mg will be equals to, so from this equation now you have to substitute y0, so y becomes y0 plus delta y, and this expression looks something like this. Okay. Now what you need to do is that here you see that, so this is the nonlinear term. So you have k into y0 plus delta y whole square. So what we need to do here is that we need to linearize this nonlinear term. So for that, what we'll do is that we'll again use the Taylor series expansion, and using that Taylor series expansion and ignoring the higher order terms, you will get a linear expression for y. So y will be equals to k y0 squared plus 2 k y0 into delta y. Now, if you substitute this value in the previous equation, so you substitute this here. So if you do the calculation, you will see that after doing the after ignoring the this mg and the corresponding y0 terms, you will end up with 0 with this equation. And if you see the normal curve, you will see that it becomes, so if this is your normal operating point, about this operating point we are actually linearizing the nonlinear spring. Okay, and the slope at this point is equals to 2k into y0. Okay, so do you have any class after this?
Yes, ma'am. Now we have a class.
Okay, fine. So then there's just only, I think, one more slide. Okay, what I'll do is that I'll share this last slide also with you. So in case if you have any problem in understanding this last portion, you can ask in the next class, or otherwise we'll just finish this module 1 now, and then in tomorrow's class we'll move on to module 2. Okay, and one more thing just before I end the class is that we'll be having a quiz next Saturday morning. Okay, so I'll post the timings and all in the group, and just to let you know that the quiz for this module 1 will be next Saturday, not this Saturday, coming Saturday. Okay, so thank you for attending today's class, and if you have any doubts, you can always ask in the next class.
Ma'am, excuse me, ma'am.
Thank you, ma'am.
Yes.
Ma'am, can be the quiz done in Friday evening, ma'am, if it is possible?
Friday evening. Okay, that I'll have to check with, because we are planning that we'll have the quiz for both the sections at the same time.
Yes, ma'am.
So I have to talk with the other faculty member, and then I'll let you know.
Yes,
Friday
Saturday we have some events, so that's why, ma'am.
Okay, so Friday second half, as in you are saying like within the like before 5:30, or
no,
like
it can after 5:30, ma'am.
In the evening.
5:30 we have a lab actually, so after
Ma'am, from 6 o'clock in the evening, ma'am, we are free, so you can keep it at 6.
Yes, ma'am.
Okay, fine. So
any day in the evening from Monday to Friday at 6.
Yes.
Okay, fine. So let me discuss with the other faculty, and then I'll let you know. Okay.
Yes, ma'am. Yes, ma'am.
Okay. Thank you.